properties of the definite integral. So just like after we described the definition of derivative, we found that there were many properties that it had. So too, now that we've described the definition of definite integral, certain properties emerge from that definition. So again, the definition of the integral, or the integral AB, integrand f of x dx, is the limit as n approaches infinity of the Riemann sum for some sampling point within the subintervals as I goes from 1 to n of the summation. So there's our definition. I calculated the x squared 0 to 2 area a moment ago with it. But this very definition gives us more than just the power to calculate areas. It also gives us certain properties of this symbol which it defines. So let's look for a moment here. If we had the integral of a to a of f of x dx, then by definition we would have the limit as n approaches infinity, I equals 1 to n. But delta x, we know that delta x is b minus a on n, where b and a are here in the limits of integration, right? They're the interval over which you're integrating. They're the interval over which you're finding the area between the curve and the x-axis. But if a is b, right, if these two values are the same, then delta x becomes a minus a. There's really a minus a sitting here on n. But a minus a on n is, of course, 0. 0 times any of these values here, no matter what the height of the rectangle is at any particular location, will not matter because its base is automatically nothing. Therefore, there's no areas to any of these rectangles, and the sum of 0, no matter how many times you do it, even if an infinite number of times, will be 0. Right? So we have an integral over, we might say a trivial interval here, right, from a to a, is nothing. Next. Integral from a to b, f of x dx. Again, it's this expression. I have to use this to show these properties. Okay, delta x, I'm going to go ahead and write as b minus a on n. Instead of just writing the delta x symbol. Because I want to manipulate it here to express another property. This should be exactly the same as with only one thing changed. And instead of having b minus a, I'm going to have a minus b. But to change this to have equals here and to change this to a minus b, I have to factor off a negative, you might say. So maybe have something like this. Negative a minus b on n. There. That's reasonable. Okay. So if you have b minus a in here, you can switch it around, have a minus b here, right? You've inverted the interval, right? Instead of traveling from a to b conceptually, from left to right, if a was a smaller value, then now you're going from b to a, is what this would be expressing. So you take the negative out to the outside of the whole limit and the summation, because that's a property of limits and summations. You can always do that. So limit moves to the outside. And the rest remains the same, except for this a minus b change. But now that it says a minus b over here, we know that's the same as changing these values here, right? When it's from a to b for the limits of integration here, it's b minus a for delta x. If that's the case, then now this must be the same as moving from b to a. right? Because we switched these two values. But we did incorporate a negative to make that happen. And that's the property. That should you switch the limits of integration, it comes with a cost of a negative. So these two things are the same. Switching limits of integration, you must negate the integral to compensate.